Hello everyone, welcome to the 12th week of Analog Communication NPTEL problem solving session. So today our topic is sampling theorem. So we will be taking on 10 problems from sampling theorem, and we will be first reading those questions and then we will solve them. So without further ado, let's start with question 1. State whether the following statement is true or false. An analog signal after sampling can be called a digital signal. So here there is a uh, cool distinction between discrete time and continuous time signals and analog and digital signal. So the difference between discrete time and continuous time signal is a discrete time signal looks like this. A continuous time signal looks like this. This is a continuous time signal. Okay. This is continuous time. Why? Because for all points in time, the value of the signal exists. But for a discrete time signal, only some only at some instances of time the signal will exist. So like this, like this, like this, like this. So this is a continuous time, and this is discrete time. The other is discrete time. So here you can see that sampling clearly converts a continuous time signal to a discrete time signal. This is the effect of sampling. But does sampling convert an analog signal to a digital signal? Well, the thing is, for a signal like say, let's take a random analog signal, not a regular periodic one like sinusoid. Let's say something like this. This is an analog signal. Now, if I sample, I will get something like this. Something like this I will get. Like this. So something like this I will get, but this is not a continuous, this is a discrete time signal, just like the previous one, but this is still not digital. Digital means there are only finite values in the y-axis, but it takes on any possible value in the y-axis. There is no restriction. So this is discrete time, just like the previous. This is a discrete time signal. Discrete time signal, but this is not digital. So we get a clear counter example that sampling does not convert analog signal to digital signal. So we can say that the first option in first question, the answer is false. The statement in question 1 is false. A television signal is sampled at a rate 30% above the Nyquist rate. The signal has a bandwidth of 6 MHz. The samples are quantized into 1024 levels. The minimum bandwidth required to transmit the signal. Okay. A television signal is sampled at a rate of 30% above the Nyquist rate. The signal has a bandwidth of 6 MHz. The samples are quantized into 1024 levels. The bandwidth required to transmit the signal. Okay. So, question 2, sampling rate sampling rate Fs is equal to 30% above. So, there is a Nyquist rate and 30% above that. So, plus 0.3 of Nyquist rate. So 1.3 Nyquist rate. And what is Nyquist rate? Nyquist rate is nothing but twice the bandwidth. So this is 1.3 into 2 into bandwidth. So 2.6 times the bandwidth. So Fs is equal to 2.6 into 6. So this will be okay. So it is 15.6. So this is as we were. So 2.6 into 6. So 15.6 megahertz. This is 15.6 megahertz. So the sampling rate is 15.6 megahertz. So there are 15.6 mega samples per second. Now each sample 16 or 15.6 into 10 to the power 6 samples per second. Now each sample is quantized into 1024 level. Each sample is quantized into one of 1024 samples. So 1024 means 2 to the power 10. So 2 to the power 10 samples. 2 to the power 1 of 2 to, sorry, this is not samples, this is levels. 1024 or 2 to the power 10 levels. So each sample is quantified into one of 1024 levels. So there are, so there are 10 different, so 1024 levels. So to represent each level, we will need 10 bits, as it is 2 to the power 10. Each level needs a 10-bit representation. So if each level needs a 10-bit representation, therefore bitrate will be bitrate will be 15.6 into 10 into 10 to the power 6 bits per second. So 156 Mbps, 156 megabits per second, or 156 Mbps. This is the minimum link speed you need. So 156 Mbps. So the correct option is B. Correct option is B. Now If the number of bits in a PCM system increase from n to n plus 3, the signal to noise quantization ratio quantization noise ratio the number of bits in a PCM system increases from n to n plus 3. Uh, so quantization noise, question 3. Quantization noise is given as quantization noise is given as where delta n is quantization error. What is quantization error? Quantization error is the difference between the value of the sample and the value of the quantization level. So, quantization error depends inversely on quantization error depends inversely on the number of quantization levels. Therefore, if we change the number of levels from n to n plus 3, if n is changed to n plus 3, then delta. Now, what is ln? Ln is the number of quantization levels. Number of quant levels. This is basically 2 to the power n. So, if n is changed to n plus 3, then delta n plus 3 by delta n, as delta and L are inversely proportional, is equal to ln by ln plus 3. So, this will be 2 to the power n by 2 to the power n plus 3, or 1 over 8. So, if this is 1 over 8, then the ratio of quantization noises Qn plus 3 to Qn will be delta square n plus 3 by delta n, as it is directly proportional to the square. So, delta n plus 3 by delta n whole square. So, 1 by 8 whole square. So, this is 1 by 64. Now, if we want to do signal to quantization noise ratio, the comparison in the signal to quantization noise ratio domain, then signal to quantization noise is defined as signal power by quantization noise power, S by Qn. So, SQn n plus 3 to SQn n is basically Q, since the signal power is remaining same, it is Qn by Qn plus 3, as they are inversely proportional. So this will be the opposite of 1 by 64, so 64. So the signal to quantization noise ratio will increase 64 times. So correct answer is D. None of these, as 64 is not an option here. A PCM system uses a uniform quantizer followed by an 8-bit encoder. The rate of the system is equal to 10 to the power 8 bits per second, the maximum message bandwidth for which the system operates satisfactorily. So there is a 8-bit encoder, and the bit rate is 10 to the power 8 bits per second. So we know there is, so the bit to sample ratio in question 4, the bit to sample ratio, bit to sample ratio is 8 bits per sample, because it is using a 8-bit encoder. So there are 8 bits per sample, and bit rate is given as 10 to the power 8. So sample rate, therefore sample rate is 10 to the power 8 by 8 sample per second. So this is 1.25 into 10 to the power 7 sample per second. Now the minimum sampling rate should be twice bandwidth. This is the minimum sampling rate. It cannot go below this. This is called the Nyquist rate, equal to F Nyquist. F Nyquist is equal to 2 into bandwidth, implies 2 into bandwidth is equal to 1.25 into 10 to the power 7, implies B is equal to 6.25 into 10 to the power 6 hertz, or 6.25 megahertz. So question 4 answer is 6.25 megahertz, B. Consider a signal that ranges from -m to +m. It is quantized by a quantizer of L levels. Then the quantization noise. Quantization noise is the whole square by 12 of the quantization error. Quant noise, Qn, is equal to So the range varies from -m to +m, and there are L levels. So the quantization error will be, delta n will be 2m minus m by L. This is the minimum error, the entire range divided by the number of L. So 2m by L, this is the quantization error. So Qn will be 2m by L whole square divided by 12. So 4m square by 12L is equal to m square by 3L. Sorry, m square by 3L square. 3m square by 3L square, as the square is over L also. M square by 3L square. So option C, m square by 3L square. M square by 3L square. The Nyquist sampling rate of sync 1000 pi t and sync 500 pi t. So there are two syncs. Nyquist sampling rate of this signal, sync 1000 pi t, and added with that sync 500 pi t. So the null frequency of sync 1000 pi t is, so this is the highest frequency. So highest frequency in this ST (1000 pi). Therefore, B is equal to 1000 pi by 2 pi. Therefore, Nyquist rate, this is 500 hertz. Therefore, Nyquist rate will be 2 into 500 is equal to 1 kilohertz or 1000 hertz. So, is it 1 kilohertz? Correct answer is D, 1 kilohertz or 1000 hertz. So, correct answer is D, 1 kilohertz or 1000 hertz. For the signal sync 1000 pi t into sync 500 pi t, where this into symbol implies convolution operations, the Nyquist rate is. So here sync 1000 pi t into sync 500 pi t. So for the next part here, convolution. Here we will do a convolution in time domain, which implies there will be a multiplication in the frequency domain. So we have two sinks. One is a sink 1000 pi t. One is a sink 1000 pi t, and another is a sink 500 pi t. So here this is a convolution. If you take it in the frequency domain, it will be a rectangle t by 500 into rectangle t by 250. So one will be between 500 to minus 500, and another, this is between 500 and minus 500, and another will be in 250 to minus 250, and these two will get multiplied. So if you multiply two signals whose only common area is this, so the resultant will be something like this, which will only exist between 250 to minus 250, because between minus 250 to 250 they are both 1, while outside 250 to minus 250 one is unity, another is 0, so the product is 0. So ultimately we have a signal which only exists till 250. So the bandwidth is 250 hertz. If we know the bandwidth, then we know the Nyquist rate. The Nyquist rate will be 2 into 250 or 500 hertz. So question 7, option C, 500 hertz. The Nyquist rate for the signal sine cube 1000 pi t into sine square 2000 pi t is, so if you take the sine to the power n or cos to the power n, then the bandwidth becomes bandwidth of sine to the power mt is a sine to the power m into 2 pi ft is nf. So the multiply the power multiplies the bandwidth. So bandwidth of, what is the expression, sine cube 1000 sine square 2000, sine cube 1000 pi t into sine square 500 pi t will be 3 into 250, 3 into 500, as 1000 byte you will have a bandwidth of 500 plus 2 into 250. So it will be 2000 hertz. So Nyquist rate will be 2 into 2000 or 2 into 2000 or 4000 hertz or 4 kilohertz. 4 kilohertz. So the correct answer is, sorry, it was signed 2000, not 500. Sorry. I have taken down the question wrong. This is 2000, not 500. So 2000 means this will be 1000. So this will be 2 into 1000. So 3500 hertz. So bandwidth will be 2 into 3500 hertz is equal to 7000 hertz or 7 kilohertz. So option C, 7000 hertz. A rectangular pulse train with width 0.25 millisecond and period 1 millisecond is multiplied with a signal xt and produces sample signal yt. Then xt can be recovered from yt by using an ideal LPF if x omega equal to 0 for. So basically they are saying that what should be the frequency of sample filter for if what should be the cutoff frequency of filter for which we can avoid aliasing. So to avoid aliasing means when samples overlap on each other. So to avoid that, the sampling width, question 9, the width of the sampling impulse width. This is kind of like the sampling rate. Impulse width is given to be 0.25 millisecond. So 1 millisecond. One millisecond. It is given to be 1 millisecond. The period, sampling impulse period, not width. Sampling impulse period is given to be 1 millisecond. So if sampling impulse period is 1 millisecond, if sampling impulse period is 1 millisecond, then sampling rate will be 1 by 1 millisecond, which means 1000 hertz. So to avoid aliasing, this 1000 hertz, this 1000 hertz should be greater than the Nyquist rate, greater than or equal to. So the Nyquist rate should be less than or equal to this 1000 sampling rate. This is the sampling rate if for Nyquist calculation for data Nyquist or data rate for data rate calculation, not Nyquist, for avoiding aliasing, for avoiding aliasing. So implies if Nyquist is less than equal to 1000 implies if Nyquist less than equal to 1000 implies 2 into the maximum frequency. What is the maximum frequency of the signal? The maximum frequency of the signal is not given. So 2 into omega. 2 into omega by 2 pi is greater than 1000. Implies omega is greater than 1000 pi. So the maximum frequency should be greater than 1000 pi to avoid aliasing. So the correct answer is option B. B for Bombay. Omega is greater than 1000 pi. 24 voice signals are sampled uniformly at 8 kHz and then sent using TDM scheme. The sampling process uses flat top samples with 1 microsecond duration. An extra pulse of duration 1 microsecond is added for purpose of synchronization. The spacing between two consecutive pulses is. So 24 voice signals are sampled at 8 kHz and then sent using time domain multiplexing scheme. The sampling process uses flat top samples with 1 microsecond durations. An extra pulse of duration 1 microsecond is added for the purpose of synchronization. The spacing between two consecutive pulses. So we need to fit 25 pulses, 24 voice signal pulses and one synchronization pulse. So we need to fit 25 pulses and they are sampled at 8 kilohertz. So So there are 24, as I have said, there are 24 voice signals. So they are sampled uniformly at 8 kilohertz and then sent using TDM. The sampling process uses flat top samples with 1 microsecond duration. So there are total 25 signals to be sent in a of sampling interval is sampling interval is 1 by 8 kilohertz. So this is 0.125 milliseconds, or this can be expressed as 125 microseconds. So if there is 125 microseconds sampling interval, then sampling duration, the sampling interval, in that we have to fit 25 signals, each of width 1 microsecond. So each signal, so in this 125 microsecond we fit 25 signals. So each signal is given 125 by 25 is equal to 5 microsecond duration. But each signal lasts 1 microsecond. So gap between two signal, 5 minus 1 is equal to 4 microsecond. So the answer is 4 microsecond. That will be all from my side for sampling theorem, and this concludes the problem solving session on sampling theorem. There will be an extra class next week which will be on a miscellaneous topic with no fixed topics. So that will be, and with that we will conclude the analog communication problem solving session. So stay tuned for the special class next week. Thank you.